Ladies and gentlemen, welcome to video number 17 in a series of video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in late 2017. This is now November 25 in the year 2018, about a year later. We will today discuss in video 17 part 4 of the Fivefold Sun as a book, which deals with the bounds of the solar cycle's length. In a first part, we will discover the notion of bound lengths, which would be akin to poloidal cycle components for the solar cycle. In video 17, we first introduce the methodological issues to arrive at a determination of the cycle bounds, and then we will describe the statistical distribution of solar cycle lengths as found in part 1. The methodological issues associated with the assessment of cycle length distribution in solar physics are well known. First of all, the solar cycle is not a sine, so Fourier analysis is not directly applicable. It has some pitfalls. We shall see if the Fourier analysis, harmonic analysis, is able to discover as much as the scrutiny of individual cycles. As far as individual cycles are concerned, cycle number 4 is also a major methodological issue. It lasts, in principle, from as a canonical point of view, from 1783 to 1798 or 99, i.e. more than 15 years, and is a single outlier by a large extent. It is proposed to split this cycle in 2 cycles, as suggested, for instance, by Uzoskin, Mursula, and Kovaltsov. Here we decide not to include this cycle so as to avoid the controversy. So we focus on 26 historical cycles as per the binning procedure that was performed in part 1 of the Fivefold Sun as a book. One of the limitations of this approach is that when a new cycle is introduced in the statistic, it is possible that it will reshuffle the binning results. So, for instance, in 2 or 3 years, we will have an additional cycle number 25, and we'll see what happens. Maybe the results that will be shown today will be somehow altered. The solar cycle length distribution found in part 1 from 26 extant solar cycles was obtained from the definition of 5 bins with half width of 0.45 year each, with a prescribed center of the entire distribution at 10.7 years. The center is a little bit too high, should be 10.615, but this is what we can do to approximate this value with a simple binning procedure. This is the table in part 1 in which these results are summed up. In fact, there are 4 such tables. This one is excluding, as said earlier, the cycle number 4. We have other tables which are the same, but with this cycle included, or with this cycle split in 2 cycles, and still other options. So this particular case is representative to arrive at this statistic. Here we have the epochs of the minima in the sunspot cycle represented by the relative sunspot number plus from the date when it was available the radio flux. And between these minimum epochs, we have here obtained in part 1 the lengths of the respective cycles. And now we sort these lengths in this column from longest to shortest. The longest is 12.5 years long and the shortest 8.9 years short. And we can now bin in smaller or larger bins. This is the largest bin that was used, and it is, as said, the 0.45 year bin. We arrive, without surprise, already shown in part 1 in the first videos of this series. The central bin with 10.6, a little bit more than 10.6 as its central median value in this bin. And it includes 10 cycles. So of 26 cycles, 10 cycles are in this central bin, and obviously they predominate in numbers. Then we have a bin here close to 10.0 year length with 7 values, and a bin here at this is the long bin, the upper end bin, which has 5 cycles. These are the 5 cycles with a central value of 12.4 years. As you can see from this list of the cycle lengths that compose this bin, they are very closely grouped around this central value. It is really a homogeneous group, and it is a large group, which is the third largest in the distribution. We can now contemplate to refine the found central values for each bin. So we shall try to consider additional information to arrive at a refined value for the top bin, 12.4 years, and the bottom bin, 8.9 here. As for the long bin, we arrive at a confirmation of about 12.4 years. And this is somewhat new because this length is not identified as such in solar physics literature, even though there are many, 1 in 5 cycles almost. And for instance, the last cycle, very contemporaneous cycle, 1996 to 2008, is one of this cycle and has exactly this characteristic length. So if you look at the sunspot number series spectra or periodograms that can be found from a meta-analysis in the literature, there are not much more than shown in here. Cole, a well-known paper, 1973, found 12.2 years. In 1983 was found 12.8. And more recently, Leif Svalgaard, now at Stanford, found 2 peaks in FFT spectrum that he published of 12.0 years and 13.1 years. These are implicit in his data. I assert these values which I found from inspection of his FFT. So in conclusion, we have nothing to speak against a value of about 12.4 years plus or minus 0.05 years perhaps. And we will see separately in part 5 and in a dedicated section of the present part 4 that in the geomagnetic index, the AA index, there is also a peak-to-peak cycle of 12.4 years, although it is not the only cycle length in the AA index. If we now turn to the characteristic length for the short bin, we will arrive at a slightly larger value of 9.05 years compared to the single cycle in this bin at 8.9 or 90 years, depending on the rounding. from consideration of the observed individual cycles. In solar physics literature, there is very, very little information on such a characteristic length. We have to go back from 2003 to a century earlier to Schuster to find this length mentioned, 9.25 years in Schuster 1906. As you know, Schuster is the man who invented the periodogram and who decided to test his invention on the relative sunspot number series, because it was at that time and is still now the longest quasi-physical time series that is available. But then we have only this team to assert a comparable result in the sunspot number series. If we want to have more detailed evidence, stronger evidence of the presence of such a period, we have to go again to the geomagnetic AA index. It has a cycle of 9.05 years since 1880. And we also find the same value as in Schuster's sunspot number series analysis in the solar wind velocity variations, 9.25 years. In part 5, we will see that there is possibly a specific poloidal cycle of such length. And we remember from the previous page that also for the long bin length we had AA and solar wind evidence that point to the possible presence of a poloidal cycle with two different periods. So we keep the value of 9.05 years, although it is relatively uncertain. On this basis, the bounds for observed cycle lengths are 9 years, perhaps 90 years, and 12.4 years. If we now translate these lengths into numbers of rigid rotations, we know that for the central value Schwabe length, it is 144 rotations. For the long bin, we would have 168.3, and this is relatively well constrained with a small error bar. And here we would have 123 plus or minus 3, which includes 121, as much as this estimate includes 169. So 169 is the square of 13, and 121 is the square of 11, as 144 is the square of 12. So we have here a hint that perhaps in the longest observed cycle bin and in the shortest observed cycle bin, there might be a square number of rigid rotations of the solar ball. 11 and 13 are odd numbers, so we have a play of words here on the notion of an oddball sun. Would it be possibly consisting of 11 balls or of 13 balls, as the standard basic arrangement is suggested here to consist of 12 balls? We have some indications that such oddball geometries are preconditions for the presence of a dipole in a sphere. With the electrostatic approach, we can see that for n equals to 12 for the number of point charges at the surface of a sphere, we have a optimal spherical code, and we have no dipole because of the regular symmetry of the arrangement. But with the symmetry break for 11 or for 13 points, we have no longer a regular arrangement, and we have a configuration which yields a non-zero dipolar field. This is what is proposed by a few authors in general literature on the Coulomb problem, alias A.K. Thomson problem. In this table, you see integers from the OEIS website, which is a repository for integer sequences for this sequence, in which is given for the number of charge points at the surface of a 3D sphere, solutions of the so-called TAMES, which is also A.K. Thomson or Coulomb problem, the number of symmetry elements, if I'm not mistaken, as given in this OEIS sequence, in which you see that there are 120 symmetry elements for the case with 12 points. This is what we introduced in part 2 as the number of elements of the icosahedral group, which is found for this configuration. But if we drop one charge point, we fall from 120 to only 10 symmetry elements. If we add 1 point, we fall from 120 to only 8 symmetry elements. So here is proposed in the bottom part of the table, is proposed in the Fivefold Sun project, the hypothesis that this high number of elements, of symmetry elements, is relevant to the presence of a multipole. And we propose that for any number of elements equal or larger than 12, we have multipoles, which is here the case for all except 7, and here for 16. But in this bottom row, we have the cases for number of elements less than 10, which is proposed as an illustration here, as a case study, to be a threshold below which we have a dipolar field with this number of point charges. So 11 point charges as dipolar, and with 13 point charges as dipolar. We have introduced the notion of an observed potentially poloidal cycle, which is discussed in part 4 of the Fivefold Sun as a book in its section 114, and will be discussed again and detailed in part 5. A poloidal cycle composed of 3 rows of cycles. The first one with 121 rotations, this is the 9-year cycle. The second one as much. And the third one, 169 rigid rotations, this is the 12.4-year cycle bin. In total, these are 411 rigid rotations, which amount to about 30.3 years, plus or minus 0.1 year. This is not new. For instance, Ahluwalia, as early as 1998, introduced the notion of the 3-cycle periodicity in geomagnetic and solar wind time series. This is even in the title of at least one of his papers. And we can see that this 3-cycle series, if you divide it by 3, it averages out to 10.1 year, to be compared with the toroidal sunspot cycle, the length of which is either 10.6 years as a median or 11.1 years approximately as a mean. So this poloidal cycle is not in phase with the sunspot cycle, contrary to what is canonically accepted in solar physics. You see some clues of this out-of-phase situation. For instance, in some of the latest epochs of the dipole peak value, which were not at sunspot minimum epoch as expected. For instance, near 1984 and near 1994. Yet, 10.1 years is approximately the central value of an intermediate bin that we showed in the page describing the statistical distribution of solar cycle lengths from part 1 of this book. And this is the secondary mode in not the poloidal but the toroidal sunspot cycle length distribution. This is also not new. For instance, Kalevi-Morsula found 10.1 or 10.2 as a characteristic length for the sunspot cycles in the relative sunspot number series more than 10 years ago. This leaves us with many open questions that we will try to answer in a later video. This is, ladies and gentlemen, the end of video 17. I thank you for your attention.